Suppose x and y are discrete random variables. If they're independent, the conditional probability is the same as the unconditional probability. Similarly, if they're continuous random variables, though the notation is going to be a little more complicated. But if they're not independent, the probabilities are different, and so the question we want to ask is, can we quantify how much the probability changes? And you might think about this as what we'd like is a measure of how much the variability of x is due to the variability of y. And this motivates the coefficient of correlation. Let x and y be random variables, with the variance of x and y being greater than 0. The coefficient of correlation is going to be, which is the covariance divided by the square roots of the variances. So let's consider some extremes. Suppose x is always equal to y. Then the variance of x is going to be the variance of y. And so the covariance will just be the variance of x. And so the coefficient of correlation will be. And remember how the variance changes when we include a constant factor. Nothing would really change if x was some scalar multiple of y for any positive value. At the other extreme, let's suppose x is negative y. Then, again, the variance of x is still the variance of y, but our covariance will be. And so that would be the negative of the variance of x. And so the coefficient of correlation will be. And again, this would be true if x was some negative scalar multiple of y. And this means that if x and y are random variables and x is some scalar multiple of y, then the covariance is 1 if that multiple is positive, and negative 1 if that multiple is negative. Now, remember, the addition or subtraction of a constant doesn't change the variance. And so our result holds if x is some linear function of y. Now, this presupposes that we actually know the relationship between x and y. If we don't know the relationship between x and y, we still want to say something about that variance. And so remember, the standard deviation forms a natural unit of measure for the random variable. The natural way to measure the magnitude of x and y would be to compute their z-scores. But since adding or subtracting a constant doesn't change the variance, let's ignore these constants where we subtract the mean of the random variables. Then let's just consider the variance of the sum and difference of these ratios. So we'll find the variance of their sum. Remember, that's the variance of the one plus the variance of the other plus twice the covariance. Now remember, any scalar multiple factors out as its square. And let's rework that covariance. That's the expected value of the product minus the product of the expected values. And we can remove the constant factors. But we see this is just going to be the covariance divided by the product of the standard deviations. Now, since the variance of x is the square of the standard deviation, and likewise for the variance of y, then our expression simplifies to Now, variance is always going to be non-negative, and so this expression has to be greater than or equal to 0, and so we find the coefficient of correlation must be greater than or equal to -1. Similarly, if we look at the difference, we find As before, the covariance of our ratios is going to be the covariance divided by the product of the standard deviations. And so, as before, this expression is going to be, and again, since the variance must be non-negative, we find, and putting everything together, this tells us that the coefficient of correlation satisfies. So we found that if y is a linear function of x, then the coefficient of correlation is going to be plus or minus 1, depending on whether the coefficient of x is positive or negative. But could the coefficient of correlation be plus or minus 1 if y is not a linear function of x? Well, let's see what happens. So the algebra that got us the variance for the difference doesn't change, and so it's still 2 times 1 minus the coefficient of correlation. But if we know the coefficient of correlation, we find, and so here we have a random variable whose variance is 0. Now, since the variance is the expected value of a square, which is always non-negative, the only way for the variance to be 0 is for the random variable itself to be a constant. So, since z is this difference, and z is some constant we'll call c, then we find, and so y is some linear function of x for some constants a and b. A similar result holds if our coefficient of correlation is negative 1, and so we can conclude that the coefficient of correlation is plus or minus 1 if and only if one variable is a linear function of the other,